Let's now proceed to analyzing the pump unit operation in the Rankine cycle. So the pump is going to deal with a change between streams 4 and streams 1. So we're going back to the beginning of the cycle. So here we're dealing with the pump. The material balance, just like the other unit operations, simplifies down into M1 is equal to M4, which is just equal to M dot. For the energy balance, we start with the open system energy balance. It's equal to Q dot. And then the shaft work here, so with a pump, things are moving, pieces of machinery are moving. So our shaft work, we're just going to rewrite as pump work. All right, so when you're dealing with a pump, the work involved in a pump is the shaft work. And then we also have the enthalpies of streams going in and the stream going out. Okay. All right, make the same sort of simplifications as before, steady state, adiabatic, and we find that the pump work is equal to m dot multiplied by h1 minus h4. Okay. We know what m dot is, and we know what h4 is based on our analysis of the condenser. But at this point, we don't know the pump work, and we actually don't know h1 either. And at this point, it would be tricky to actually figure out what h1 is, because we go back to the stream pictures. We know the pressure, but we don't know the temperature. And we also don't know what state the steam is in at this point, right? Whether it's saturated, superheated, or even if it's saturated, if it's pure vapor, pure liquid, or something in between. Okay? And so, the pump analysis at this point, we can't really directly use the steam table. So we'll have to try another strategy. And what we could do here is we could actually use an equation that is specific to pumps. And so the way that would work is, let's think about the units of the pump work. So here we're dealing with watts. And a watt is equal to a joule per second. Equivalently, you could say that it's equal to meters cubed per second multiplied by joules per meter cubed. Okay? And so meters cubed per second, that's a volumetric flow rate. And joules per meter cubed, if you remember, that's the same thing as a Newton per meter squared, or in other words, a Pascal. And so joules per meter cubed gives you a pressure. And so with pump work, the other way that you could calculate it is actually just by taking your volumetric flow rate of the steam and multiply it by the pressure change of the steam as it passes through the pump. Okay? And so this equation, if this is the first time you're seeing it, don't worry, because you'll deal with this equation a lot in your transport phenomena class. Okay? All right. So rather than just using the regular energy balance to calculate pump work, instead we could use an additional equation that is just typically used to calculate pump work. Okay. All right. So with that equation, let's adapt it to our system. So we have our pump work. It would be equal to some volumetric flow rate multiplied by delta P, right? So that's final minus initial, or outlet minus inlet. So our outlet is stream 4, and our inlet is, or our outlet is stream 1, and our inlet is stream 4. So we have P1 minus P4 there. For our volumetric flow rate, we don't know that one directly, but we could write that one in terms of the mass flow rate, which we do know, multiplied by some sort of specific volume. Okay. Right. So we know this and we actually know these as well. For the specific volume, there is a nuance here because you know we have two different streams that we're dealing with. But typically in these sorts of pump calculations, what's typically done is you use the specific volume of the input stream. So typically use input stream value. And the reason for that is because with this pump, we're dealing with a liquid, right? And one of the classical assumptions that we always make is that a liquid is incompressible, right? And so consequently, the volume shouldn't really change as a function of pressure, right? If you look in the steam tables even, and you look at the specific volume of different uh, the pure saturated liquid at different pressures, um, the value shouldn't really change that much as you go to that different pressures. And so that seems to mean that this assumption is okay. It's going to be a decent approximation. Okay. All right. So based on that idea, we could plug in to calculate our pump work. We know the mass flow rate. We could use the specific volume of the saturated liquid water in stream 4. And so that's about this value. So you could confirm that using the steam table yourself. And then we're going to punch in our different pressures. I'll write this in units of joules per meter cubed. And what we get is that the pump work is going to be equal to 74 kilowatts. Okay? And so this is compared to the work that's exiting the turbine, this pump work is much smaller, right? Because for the turbine, 10 megawatts were leaving. For the pump work, right, this is positive, so this means this is the work we need to put into the pump. But it's a relatively small amount compared to the turbine. In any case, now that we have the pump work, we could go back to our energy balance. And at this point, we now are only dealing with one unknown. So H1 is just going to be equal to WP dot over M dot plus H4. What we get is H1 is just equal to this. So we have our H1 value. One other thing, just for completion's sake, we could also do the entropy balance. There's no heat. And since we're assuming this entire process operates optimally, we're not dealing with any S-gen. So what we find is that, also steady state, what we find, just like with the turbine, S1 should be equal to S4, and we get these values for the entropies. Okay. All right, so let's collect this information. And here, 260.5, 0.8320, and for the pump, just 74.3. Okay. All right, and so that's the analysis for the pump. And very easily at this point, all we have left is the boiler. So let's do that analysis. Okay. So this is dealing with step 1 to 2, boiler. Material balance, same as always. On the energy balance, We're just going to start with the open system form of the energy balance. Okay. Steady state, the boiler has no shaft work, and what we're dealing with is Q dot. And in this case, just to remind you about the picture, with the boiler, we're looking at the heat going into the Rankine cycle, so we're dealing with QH. QH is just equal to m dot multiplied by H2 minus H1, right? And at this point, we know everything on the right-hand side. So all you do is plug in. All right, so we have that value for QH. And I won't go over here, but if you really wanted to know what the temperature of stream 1 is, you could use the steam tables to do that. That's not necessarily necessary for this problem. Okay, so let's collect our information. So what we have is the change in enthalpy for the boiler step is 2.6 e to the fourth, 2.6 e to the fourth for the heat. Okay. All right. And now that we know, all the different parts of the Rankine cycle here, what we can now do is we could actually calculate the efficiency of the cycle as well. Okay. So the efficiency, eta, which rank, so Rankine cycle, here it's going to be your negative W total divided by the heat put into the cycle. And that negative W total is going to be the difference between the turbine work, or WS here, minus the work needed in order to operate the pump, right? Because that basically like subtracts from the overall uh, energy needed, or that, I mean, this gives you the total, essentially. Okay. All right. And so what we find here is we have negative 10 e to the 6 watts minus 7, 4.3 e to the 3 watts. That's going to be divided by 2.6 e to the 7 watts. And we find that the efficiency of this Rankine cycle is 0.38. So 38% of the heat that we put into the cycle, we could actually extract as shaft work from the turbine. To give a basis on whether how this compares to if we tried to use a cycle that was based on the Carnot cycle, right? So that's the maximum possible sort of efficiency that one can achieve. What we could do is we could just say the Carnot efficiency is 1 minus T3 over T2. And we find that, or 1 over, yeah, yeah. So the T3, that's the temperature of the cold stream, and T2 is your temperature of your hot stream, essentially. Okay. And we find that based on that temperature difference, if we designed a Carnot engine around that, we would actually get a efficiency of 58%. And so even in the best case scenario, the Rankine cycle, right? So here we said this is going to be the optimal sort of operation of the Rankine cycle, right? There's no inefficiencies with a turbine, condenser, pump, or boiler. And even if there's no inefficiencies there, we still find that the overall efficiency of the cycle is much lower than the Carnot engine. Okay, so this is the best case of what one could achieve with for a ranking cycle with these specific operating conditions. But in reality, you won't even be able to reach that maximum value, right? Because in a real Rankine cycle, which Rankine cycles are actually used in power plants and things like that, you actually do need to deal with irreversibilities, right? So things like friction and other irreversible phenomena, you're going to get an even lower efficiency. So eta rank actual, it's going to be even lower than your eta rank if you're dealing with a truly reversible process.